Okay, so let's do a non-symmetric bending problem. I've got this extruded aluminum section here, basically a square with these little tabs on either tabs located here and here. We are going to try to figure out what the maximum moment that we can apply about the z-axis here if the bending stress needs to not exceed 12 ksi. So I'm just gonna go have a look at this. So we got the cross section that we're looking at reproduced here. So the first thing we're going to want to do is we're going to want to find the IYs and IZs. And that's in relation to the original coordinate system that was put in place. So our y-axis is here, our z-axis is here. Obviously, x-axis comes out this way. So we need to find those initially, and then we're gonna transform those later on. Because essentially, when you're doing unsymmetric bending problems, you always want to be working using the IYs and IZs, and also the of the prime axes. So you're gonna have to find IY, find IZ, and also you're gonna need to find your IZY and use that to figure out where the prime axis for this cross section is, and then from there basically transform your coordinate system. But anyways, so relatively straightforward for figuring out the IY and IZs for this cross section in this coordinate system. So we broke it up into 3 sections here. Green section in the middle, and A2, A3. I got these areas. I got these centroids. This one's located. For this one, it's located 0.6 down and 1.05 this way. Obviously, the opposite on this side, so plus 0.6 minus plus 0.6 in the y, minus 105 inches in the z. IZ and IY primes, so that we're going to be using to invoke basically the base that we're working from. And then we need to also have our parallel axis theorem. So we got when we're finding out the IY, we add together the IY primes, and then we also add together the area times the times the z distance in this case, because we're working in the zy plane. Again, our area times that, and then I just multiplied that by 2 here because that's going to be identical for A2 and A3, since the only term that would change would be switching the sign on the z, but we square that anyways, so that goes away in the wash. So we end up with an IY of that 0.8296 inches to the fourth, and then IZ in the similar manner. We add up our IZ primes, so that's those. Invoke our parallel axis theorem, and then we're just using the y distance here, squaring that, and then again just multiplied by 2 because the only thing that changes is the sign on the y, which when you square it goes away. So we got that for our iz. So respectively, that is saying that this value here is the z is the I that you get for rotating about that axis, whereas this is what you would use for rotating about this axis. So it's not surprising that that one's larger, because again, it's kind of got the bits that are a bit more further out. So we also need to find our IZYs in order to figure out what our prime axis is, and also to figure out what the IZ and IYs are at those prime axes. So again, because the base structures here, the base cross sections are all they're all symmetrical about either the z or y axis. So these don't have any inherent asymmetricalities. So the only thing that affects stuff here is the parallel axis theorem portion, and the box in the middle doesn't do that at all either, because again it's centered on the centroid. So essentially we just get to the area of this. We'll start with the A2 area of this times the times the z and the negative y. So again, our negative 0.6 times our 1.05 inches. Again, keeping in mind that based upon our coordinate system, this is positive for z. And then we repeat on this side, which ends up being the same value because the signs on both the 0.6 and the 1.05 inch terms get repeated. They both switch. So we end up with this value here, 0.2268 inches to the fourth. That should be to the fourth. And then we can find our prime axes from that. So we got our tan 2 theta prime is equal to minus IZY divided by IZ minus IY over 2. So I just moved the 2 up to the top. Got the negative sign here and the negative sign here, so that those two cancel out. But then we got to the smaller value minus the larger value down on the bottom here. So that ends up being negative 0.1647. Again, the units on there is it's a ratio. So if you end up having some units left over at the end, then you've got some issues that you should resolve. We can just take the inverse tan of that and divide by 2 to get our theta prime. And that gives us a negative 29.4 degrees. So again, keeping in mind that we're working off, y's in this direction, z's in this direction. So we're working off kind of rotating from the z-axis. So we're rotating downwards, rotating our z-axis downwards 29.4 degrees. So these are our new prime. These are our prime axes. Right here is our new prime z-axis, and here's our new prime y-axis. So we need to find out what the i's are about those axes. Again, just use the formula that we worked with before. Iz prime. So that's the I about this axis. That's the average of those two, of the two initials i's that we calculated, plus the difference between the two divided by 2 times cosine 2 theta prime minus our IZY times sine 2 theta prime. So plugging in values here, I'm not going to talk too much about that. We end up getting a value here of 0.4226 inches to the fourth. So again, that is about this axis. So again, this axis is oriented kind of inline, so it's kind of capturing, it's slanted so that it would get kind of, so that these protruding sections are kind of as close to that axis as possible. So based upon that, we expect to see the I a minimum there. And then we've got kind of the opposite for our IY prime. It's still just base it upon the average, but then it's minus this term that was positive over here, and then plus this term that was negative up here. So we end up getting a maximum value for the I. So essentially, what we're saying here is we have this axis here, and if we're trying to rotate, bend about this axis, the fact that we've got these bits here that are basically as far as possible from that axis as you can get, that results in an I y prime that is at its maximum. So this is our I minimum, this is our I maximum. So the next thing to do is to find the neutral axis. So now we've got our IZs, we got our IZ and we got our IY for the prime axes. I will want to emphasize this. The textbook kind of doesn't make it all that clear, but when you are doing a bending problem, like an unsymmetric bending problem, you need to be working in you need to be working off the prime axes for the cross section in question. So if you have if the problem has the cross section itself that is unsymmetrical, then you're going to have to do this transformation first, and then after that you can figure out how the moment affects things. So we want to find the neutral axis. The moment was about the original z-axis that we're applying, so we need to basically figure out what it is relative to the prime z-axis. Again, we've got the prime z-axis here, and the moment that was going on there, then this is a positive rotation of 29.4 degrees. So we got this formula here that we use to find the neutral axis. Our tan alpha is the angle of the neutral axis relative to the prime axis in question, is equal to our IZ divided by IY times tan of the angle of the moment relative to the prime axis. So that gives us 14.1 degrees. So that's this angle right here. 14.1 degrees is this angle here. It's relative to that axis. Relative to that axis here. So relative to the original z-axis, it's 29.4 minus the 14.1, which gives us 15.3 degrees. Is going to be that distance there. So again, here's our neutral axis. And we basically also need to determine what the moment is relative to the, in terms of the, in terms of rectangular components parallel to the prime axes in question. So essentially we got our m naught here, and we got something parallel with our new prime with our z, our new z axis. Got something parallel with our new y axis. So again, if both of those are going to be positive in order to result in something that goes like this: positive in this direction, positive in this direction. So both we can figure out what those are. So the z component, z component there is just going to be cosine of the 29.4 degrees times the moment, which gives us 0.871, and then the y is just the sine of that. So 0.491 times our m naught. So in order to we know that the maximum stress levels occur at points that are the maximum distance from the neutral axis. So looking at this, we got our neutral axis. Got our neutral axis here. I'm drawing lines that are parallel out from that neutral axis. Well, okay, so we can look at that and we can see, hey, there's 2 points that are going to be a maximum distance from that neutral axis. We got this one here, and we got this one here. So again, those are going to be equidistant from one another, and essentially what that means is that the magnitude of the stress is going to be the same, but the directionality of it is going to be different. So essentially, if we're applying a moment about this axis, then we expect this to be under compression and this to be under tension. So we got the locations in the original coordinate system. So location of this one here is at a positive y prime of 0.75 and a negative and a positive z prime of 0.75, and then over here the opposite, minus 0.7, minus 0.7. So how to translate to our prime axis coordinates? I decided to go with a diagram approach. So essentially just got 0.7 here, we got 0.7 here, got the angles in question, we got our prime, got our new y-axis, we got our new z-axis. So essentially just kind of examining what sort of triangles we can measure off this one. So based upon that, we can, we know that, which means that we can calculate this. So that gives us this distance here. We can also calculate this, which means that we can figure out what this distance here is by subtracting 0.7, by subtracting this from 0.7 0.75, which means that once we have that, then we can calculate this, which combined with this value here gives us our new y our new y coordinate, and then we can also use that to calculate this distance here, which is just our x coordinate. Sorry, our z coordinate. So yeah, that's a kind of a more graphical approach to calculating the new location based upon the rotated frame of reference. I'm sure that there's also a relatively simpler formula that you could look up somewhere to do that. But anyways, so anyway, we have our prime axes. We know what the prime axis is. We know that locations are in terms of those prime axes, and we know what the moment is relative to the prime axis defined, so we can solve for our stress induced. So we have our stress levels, again, just taking the formula from the textbook, minus the moment about the z-axis times the y-coordinate divided by the iz, again, prime. And then plus the my times the z location divided by iy prime. So again, all of these are in terms of the prime axis coordinate system. The z, the locations are, the i's are, and the moments need to be. If you're not working in your prime coordinate system, then this ain't gonna work. So just plugging in values here, we can solve for our stress in terms of a moment. Both point A and point B, the magnitude will be the same, the directionality will be different. So at point A, it's going to be negative. At point B, it's going to be positive. So if we know what our maximum stress level is, it's 12. Then we know the maximum stress level is 12 ksi, then we just insert that into this equation here. So we got 12 ksi is equal to 1.94 times m naught divided by inches to the third. So solving for m naught, I just divide by this value here. So 12 ksi, I decided to put that in terms of, I decided to push it out to 12,000 pounds per square inch, divided by the 1.94 per inches to the third. So 2 of those inches cancel out, which leaves us with 12.19 kip inches, or if you wanted to divide that by 12 to give us 515 pound-feet. So that's the maximum bending moment that you can apply to this sucker about this axis without causing the stress level to exceed 12 ksi.